All right, everyone, thanks for coming today. So I will be talking about the abundance and vertical distribution of Cephalopod Paralarvae in the northern Gulf of Mexico. So paralarvae are young cephalopods. The paralarval phase is the first stage of the cephalopod life cycle after hatching. Paralarvae have distinct adaptations that allow them to live in the plankton community, and they are morphologically distinct from older conspecifics. And the paralarval phase lasts until the individual has developed those adult morphological characteristics and behavior. Now, most paralarvae tend to have very small sizes, even those that have large body sizes as adults. So a common Gulf of Mexico squid, Abralia, is about 1 millimeter in mantle length at hatching and becomes a juvenile at about 11 millimeters in mantle length. Partly due to these small sizes, most paralarvae cannot swim against horizontal currents. They are zooplankton after all, but they can swim vertically within the water column. And because they can swim vertically within the water column, they have the ability to perform diel vertical migrations, which have been recorded in some species, such as the inshore squid species, Doryteuthis opalescens. So the motivation of this research is that learning where in the water column paralarvae are located allows us to make some inferences about the conditions, like water temperature or light levels, that they exist in, and also how likely they are to be transported away from the location of hatching by water currents. So I had three main objectives here. First, I wanted to compare the average abundance for each taxon between daytime and nighttime samples, between depth bins during the day, and between depth bins at night. Next, I wanted to identify any significant differences in mean abundance between these different groups, so day and night and depth levels. And third, to determine the abundance-weighted mean depth for each taxon in day and night. So the samples I analyzed were collected by the Southeast Area Monitoring and Assessment Program, or CMAP, over 6 plankton surveys. I used 2 cruises from 2009, 1 from 2011, and 3 from 2012. The samples were collected at the sites shown on this map here, and up to 8 samples were collected per site, although more commonly 5 or 6 were collected. The samples were collected between the surface and 130 meters using a multiple opening closing net and environmental sensing system, or MOCNESS. And the MOC consists of several different nets, each with its own caught end. And as you pull the MOC up through the water column, the different nets open and close so that you have several samples collected consecutively through the water column at the same site. After the samples were collected, the cephalopods were sorted out and sent to me, and then I identified them to the lowest taxonomic level possible. So to analyze the vertical distribution of the paralarvae, I started by sorting my samples into the depth bins listed here, or removing them from the dataset if they didn't fit into any of these 6 depth bins. I then split the samples into groups and calculated the mean abundance and standard error for each of the groups. And the grouping factors I used were time of day, which had 2 groups, day and night, and then depth during the day, which had up to 6 groups, which are 6 depth bins, and then depth at night, again with 6 groups. I then looked for significant differences in between levels of these groups. And finally, I calculated the day and night abundance weighted mean depth, which is a simple way to summarize the vertical distribution of the paralarvae in the sample portion of the water column. So in total, I processed 637 samples, and 30 of these did not fit within my 6 depth bins, and so they were removed from the analysis. There were 2,136 paralarvae in that subset of 607 samples that I used. And all of the analyses that I'm going to talk about were performed at the family level, as only a small percentage of the paralarvae could be identified to a lower taxonomic level. Additionally, about 30% of the specimens could not be identified to family level, so I'm not going to use them in the analysis I'm talking about here. Of the remaining, I identified 21 different cephalopod families. 5 of these had more than 100 individuals identified to them, while 11 had fewer than 10. Now we're going to look at the comparison of depth aggregated day versus night mean abundance. So on the y-axis, we have mean abundance in number of paralarvae per 1,000 cubic meters, And along the x-axis is the taxa that had more than 10 individuals collected. The light blue bars are the daytime mean abundance, and dark blue are nighttime mean abundance. So to test whether there were significant differences in mean abundance, I used a Wilcoxon test with an alpha of 0.05. And I found that while none of them had the exact same abundance between day and night, only these two families, Loliginidae and Pyroteuthidae, had significant differences in mean abundance, both with higher mean abundance during the day than at night. So now we're going to add the next layer, which is depth. And adding depth gives me a lot more groups, but that decreases the sample size per group. And that can have an effect on the standard errors. So what I'm showing here is examples of 3 taxa to kind of illustrate this. So on the left, we have depth band from 0 to 130 meters. And then on the X, we have paralarval abundance. And all 3 of these plots have different ranges of abundance, so they are not comparable in that sense. So the light blue bars are the range of abundance during the day, and the dark blue are the range at night. The dark blue and light blue points, again, are individual abundances for the samples, and the red points are the mean abundance. So what I want to get at here is kind of the variability in both abundance and number of samples per group. So here in the Octopodidae, you can see that the range in abundance is pretty small, and most of these depth bins have a similar number of samples. However, for Enoploteuthidae, the abundance really ranges a lot. Most of them have a fairly low abundance, but then there's a few high abundances that are going to have an impact on the mean abundance. And then on the right, Ommastrephidae, you can see that there's a lot of samples in those surface depth bins, but there's not nearly as many in the lower depth bins, which again is going to affect the mean abundance and standard error that we see later. So now we're going to look at the comparison between daytime and nighttime mean abundance. So this example taxa is just to get you oriented to these vertical distribution plots. On the y-axis, we have depth from 0 to 130 meters, and on the x-axis is mean abundance, and it's increasing in both directions from the center. The light blue are the daytime mean abundance, and the dark blue are nighttime mean abundance. So now I'm going to show figures, the taxa with more than 10 individuals collected, and we can look at the differences between these taxa. So what we see here is that for most of these taxa, abundances tend to be higher in the water column, and there's even a few taxa that are not collected at all in these deeper depth planes. So there's a lot to look at here, just visually comparing, but I also wanted to test for significant differences, and I did that using a Kruskal-Wallis test. And if the Kruskal-Wallis test produced a significant p-value, I followed up with a Dunn's test with Holmes p-value adjustment on all possible pairs of depth bins to figure out exactly which depth bins had different abundances. And I found that only 2 families, as well as this group of all paralarvae, had significant differences in mean abundance. So first, looking at the group of all paralarvae, I found that the mean abundance between depth bins differed significantly both during the day and at night. But the Dunn's test with p-value correction only identified 2 pairs of depth bins with significant differences. The 0 to 20 meter bin and the 20 to 40 meter bin had significantly higher abundance at night than the 80 to 100 meter depth bin. Moving on to Octopodidae, only the depth bins at night had significantly different mean abundances, but the Dunn's test with p-value correction didn't identify any pairs of bins with significantly different abundance. And lastly, for Pyroteuthidae, again, at night there were significant differences in abundance, and the Dunn's test identified 1 pair of depth bins. The 0 to 20 meter bin had significantly higher mean abundance than the 100 to 130 meter depth bin. So these plots, besides looking at them for differences in mean abundance, we can also use them to look at patterns of possible diel vertical migration. So going back to this all paralarval plot quickly, we see that the maximum abundance during the day is in that 40 to 60 meter bin, and at night it's slightly higher in the 20 to 40 meter bin, which could suggest that the paralarvae are migrating up in the water column at night. This shows the same pattern with the highest abundance in the day in the 40 to 60 meter bin, and at night in the 20 to 40 meter bin, again suggesting that they migrate toward the surface at night. And lastly, the Pyroteuthids are fairly evenly spaced abundance during the day, but at night, that top bin, the surface bin 0 to 20, has a higher abundance than the others, suggesting that these paralarvae migrate to the surface at night. Finally, I calculated the day and night abundance weighted mean depths for each taxon. And on the x-axis, I'm showing the taxa with more than 10 individuals collected, and on the y is depth from 0 to 60 meters. The light blue bars are daytime, and the dark blue are nighttime depths. So this is showing that for most of these taxa, the abundance weighted mean depth, or center of biomass, is deeper during the day than it is at night. We only have 2 exceptions to this, Ommastrephidae and Octopodidae. And for most of these taxa, the difference between the day and night center of biomass is pretty small. The largest difference is about 17 meters, and that is for Octopodidae and Argonaudidae, which have a center of biomass 17 meters deeper during the day than at night. And this information also supports the hypothesis that these paralarvae perform diel, or some taxa of paralarvae perform diel vertical migrations. So to conclude, many taxa showed high variability in abundance, which may have contributed to few significant differences in mean abundance. Most families had a deeper abundance weighted mean depth during the day than at night. Again, the exceptions were Ommastrephidae and Octopodidae, with deeper centers of biomass at night. And the differences between day and night centers of biomass were generally pretty small. And finally, apparent diel vertical migrations varied from no evidence for migration and some taxa showing a rise to the surface at night. So I'd like to finish by thanking the CMAP crew and processing personnel for all their efforts in collecting and preparing these samples that I used, as well as the Anne and Werner von Rosenstiel Fellowship in Marine Science and the Norman Blake Endowed Memorial Fellowship in Marine Science. And now I'll take questions.